We'll get started in a minute, guys. We'll get started in a minute. I'm just going to kind of go over a bunch of random stuff about what's on the test, IMFs, periodic tables, some things that maybe weren't on the warm-up today because I didn't want to make the warm-up unnecessarily long. So we'll get started shortly.
Realize how loudly you walk when someone's live streaming.
Periodic trends, bonding, polar versus non. I don't know if we're going to go over everything because based on the warm-up today, I think we're doing a fairly good job at drawing these things and picking up who's polar, who's not polar, but we'll go over what we can. I definitely want to hit the periodic trends because we didn't really talk about it today. I definitely want to talk about IMFs because people are always confused by IMFs, and we'll get started. If you have any questions, feel free to text me on Remind. I'm not going to make this too long, definitely under an hour. I don't want to go forever. Is there another link? Okay, let me try to resend the link out. Maybe this one wasn't working. Let's see. Try to resend the link out.
You want to come here?
This one wasn't working.
You want to come here? Come here. No, you're staying. Okay.
Tried that one. I think hopefully this one's working for those of you that are like subscribed and wondering where the video is and why it was a 30-second video of nothing. So we'll get started soon just to get people tuned in since I apparently sent out the wrong link. So we'll get started in a minute. We're going to really focus on periodic trends, IMFs, that's a big one, and then slightly hit on bonding and polar versus non-polar, just because we went over that a little bit with the warm-up today, and I don't want to spend too much time on the same thing over and over and over. But, like I said, if you have questions, just message me on Remind. And, yeah. So, we'll start with periodic trends, because that wasn't on the warm-up today, and I think that would be a good idea to kind of go over. So there's three main ones. We got ionization energy, which is the energy needed to remove an electron. So if you have any questions dealing with how much energy does it take to remove this outermost electron from this atom, whatever the atom may be, sodium, fluorine, silver, doesn't really matter who. That's talking about ionization energy. The trend you can look up on table S if you ever need to, but it increases this way and that way. So these are the directions where ionization energy is increasing. So it increases up a group and to the right across a period. But like I said, you can look up these values on table S, so you don't have to worry too much about memorizing them. And that's ionization energy. Electronegativity is a big one because it's used to explain a variety of things. So electronegativity is all about attracting electrons. So it goes hand in hand with ionization energy, because ionization energy is energy to remove an electron. Electronegativity is the strength or attraction for electrons. And if you have a high electronegativity, that means you really want electrons. It will also mean that you don't really want your electrons to be removed. So you're going to have a high ionization energy, because if you don't want that electron to be removed, it's going to take a lot of energy to remove it. So it's also going to increase in the same direction as ionization energy. But you can also look it up on table S, because the other thing with electronegativity that comes up often is how polar is something. Basically, how polar is this bond? And the further apart the electronegativity, the more polar it is. So, negativity of 2 bonded to something with electronegativity of 4, that's a very polar bond. But if you had electronegativity of 2.1 and you were bonded to something that had electronegativity of 2.5, that is not a very polar bond. Still somewhat, ever so slightly polar, but not as polar as the first example. So the further apart their electronegativity is, the more polar they are. Obviously the reverse is true. The closer together their electronegativities are, the less polar it is. If their electronegativities are the same, that means the difference is 0, then it's not polar at all. Atomic radius. So how big is the atom? So the size of the atom. The bigger the atom, the bigger the radius. When we're talking radius, think of like a Bohr model. We have our electrons on the outside. Our nucleus is there in the middle. Literally, this radius here, like a circle, is the atomic radius. Again, you can look these up on table S, but they increase to the left across a period and down a group. So it's the exact opposite of your ionization energy and the exact opposite of your electronegativity. Other things about the trends is explaining the trends. So the why. Why do we see these trends? Why does the electronegativity increase to the right? Why does atomic radius increase going down a group? And the explanation will always be the same. For your periods, the explanation for the trend going that direction, to the right, we have more protons. Obviously, it's a bit more complicated than this, but generally speaking, you have more protons. That's an increase in your nuclear charge. And when you have that increase in your nuclear charge, they are going to attract the electrons more closely to the nucleus, because protons are positive and these electrons are negative. And if you're attracting those electrons closer to the nucleus, well, it's going to be harder to remove the electron, which is a high ionization energy. You're attracting the electrons strongly, high electronegativity, and since they're closer to the nucleus, you have a smaller radius. So left to right, the trend explanation remains the same. You have a higher nuclear charge, attracting those electrons more closely, causing those trends to be what they are. Increasing ionization energy and electronegativity, but decreasing radius. Now for the lovely groups, going down this way, yes, the protons are also going up, but you don't see the same trend left to right. So there must be something else happening here. Can't just be the protons, because the protons are increasing down the group, but you're seeing the reverse in the trends. And that is because there are more electron shells, or more energy levels where these electrons are. Because if you're going down a group, let's say that's your nucleus again. That would be like a hydrogen atom, a hydrogen atom. Then you get down to lithium, sodium, potassium, etc., etc., etc. The electrons are occupying energy levels or shells further and further and further away. So when you go down a group, you see more of these electron shells. That means you're going to have a decrease in ionization energy because the electrons are further away. You're going to see a decrease in electronegativity because the electrons are further away. And you're going to see an increase in radius because the electrons are further away. So, same explanation for those trends, just different contexts. Groups versus periods. P for protons, periods. Electron shells for groups doesn't work quite the same way, but if you remember the proton one, then hopefully you'll just remember the other ones about electrons. Speaking of atomic radius, before I forget, excuse me, what about ionic radius? So, your atoms versus your ions. So we can take sodium atom and a chlorine atom versus a sodium ion and a chlorine ion. So what happened in this transition stage where sodium went from Na to Na+, and chlorine went from Cl to Cl-? Well, this way, you lose an electron. And this way, you gain an electron. Because electrons are negative. So for any atom to remain the same and become positive, you can't gain or lose protons because then the atom would change. So you must have lost the other thing that's charged, which is your negative electrons. And when that happens for sodium, sodium's going to get smaller. Because not only have you lost electrons, but you have lost electrons from your furthest energy level, therefore losing an entire shell, because sodium's electron configuration is 281. You lost that one electron in that last shell, therefore losing that entire energy level, and you get smaller when that happens. And that's true for all positive ions. You're always going to get smaller. Versus chlorine has gained an electron to become a negative ion. And since it become a negative ion by gaining an electron, it's easy to see that it becomes bigger. Now, they didn't actually gain an electron shell here. Chlorine's electrons are still occupying the same energy level they were when chlorine was an atom. But since your electrons are starting to outnumber your protons, not only are you breaking that attraction from the nuclear charge, but you're getting that repulsion between all those electrons. So they repel each other and make the ion look and seem just a little bit bigger than the atom was. All right. Let's talk about IMFs. Now, a couple students in my first block that might be watching, we're going to go a little bit more in depth than we do in class, so I'm going to cover the basics first. Once I start talking about stuff like dispersion and dipole, you might get a little confused. Think to yourself, well, I haven't seen that before. And you know what? That's totally normal, so don't worry about it. So, IMFs. People are always generally confused about what an IMF is. So let's kind of draw particle diagrams from like way back in unit like 2. And I'm doing my best here. I'm not that artistic, especially with my finger on an iPad. But here it's pretty easy to see that we have a solid, and here we have a gas. The question is, why is the substance on the left a solid, and why is the substance on the right a gas? It's not just because. There has to be a reason. You can't just say, oh, because ice is ice. Ice is going to be a solid at that temperature, but oxygen will not. Oxygen is going to be a gas. But why? Why is oxygen a gas at room temperature? And why is the iPad I'm holding in my hands a solid? And that's because of IMFs. IMFs is all about the attraction between molecules. And that attraction helps determine the phases, because the more attracted they are, the less entropy, the more ordered, the more likely they'll be a solid. So this solid, we would say, has stronger IMFs, whatever the substance is, than this gas, which we would say has weak IMFs. Because the weaker the IMF, the weaker this intermolecular force is, the weaker the attraction is, therefore the more likely it'll be a gas. Versus the solid's going to have really strong IMFs because they're really close together, they're really ordered, and they're highly attracted to each other. So it's more of a solid. So the stronger your IMF is, the more likely you're going to have a high boiling point / melting point, the more likely you're going to have a low vapor pressure. And the only way you can determine the strength of an IMF, or the strength of an IMF in any substance really, is from data. You can't just say this has strong IMFs. You don't know. You need data, you need observations. And those observations are high boiling point, high melting point is a strong IMF, a low vapor pressure is a strong IMF, the tendency to be a solid is a strong IMF. Stuff like that. Why is this a gas at room temperature? Oh, it has weak IMFs. Why is this boiling at such a high temperature? Well, it must have strong IMFs. Now, the one specific type that we always need to know is hydrogen bonding. And hydrogen bonding occurs in a substance that has an H with an F, an H with an O, or an H with an N, because it's fun. Like fun, ha ha ha. So, since hydrogen bonding is fun, we must see it in any substance with this bond in it. And this is just an unusually strong intermolecular force. It's not necessarily the strongest, but all else being equal, it is a strong intermolecular force. So for example, in the warm-up today, you were comparing methane, which looks like this, with methanol, which almost looks the same. The only difference was this was an OH instead of just an H. And that one simple OH, that one little thing that barely changed the molecule, completely changed the boiling point. This negative 160, and this boiled at positive 60. And that's because of hydrogen bonding. Because, again, all else being equal, if the substances are of similar sizes, very similar looking compounds, the hydrogen bond will cause that boiling point to just appear unusually high. But you can't just say hydrogen bonding is the strongest. It's just usually why we see unusual cases. So, for example, another one is H2O versus H2S. On the periodic table, S and O are right near each other. O is directly above S. But H2O boils at like 100 degrees, and H2S boils at like negative 100 something, I don't remember. But it's a much, much lower temperature than water. Even though O and S are extremely similar. They're in the same group, so they have same properties. They have the same valence electrons, which makes them similar. But water boils at well over double hydrogen, dihydrogen sulfides boiling point. And that's because of that HO, that hydrogen bonding. So all else being equal, hydrogen bonding just explains why some substances have unusually high boiling points. But the other IMFs that you just need to know, the other types, all right, in first block, just be mindful. There's dispersion forces, And dispersion force is just this weird interaction between electrons. So since every substance has electrons, all molecules have dispersion forces. All of them. Whether you're polar or nonpolar, you have electrons being shared, you're going to see these dispersion forces. And it's just this really weird, unusual movement of the electrons causes them to be somewhat attracted to each other. But I'm not going to get too much into what a dispersion force is. You just kind of need to know that they exist, and that they exist in all molecules. There's dipole, which is in polar molecules only. So polar molecules have dipole forces and dispersion forces. Nonpolar molecules only have dispersion forces. So dipole, again, all else being equal, is a little bit stronger than dispersion. Not always so, but typically polar substances are going to be a bit harder to boil than a nonpolar substance of equal size and similar properties. There's ion dipole, which is like what we drew in the warm-up. So you need to kind of understand that if you have a positive substance that you've dissolved in water, like NaCl aqueous, you just need to like understand, how is this dissolving? Like, we also dissolve sugar. That dissolves a little bit differently in water. But how is the NaCl dissolving in water? What is causing it to dissolve? So the ions split apart, so you have Na pluses and Cl minuses, and they split in water, they dissociate in water, and the Nas are going to attract all the oxygens in water, because oxygen is more electronegative, and the chlorines are going to attract all the slightly more positive hydrogens to itself. And that's an ion dipole IMF. So that attraction between a polar substance like water and an ionic substance like NaCl is an ion dipole. But for this, you really just need to be familiar with how does that look when it's dissolved in water. That's really it for IMFs. You need to be familiar with hydrogen bonding. You need to be able to look at data and use the data to determine the strength of your IMF. Hydrogen bonding is fine. And if you don't have a substance with hydrogen bonding, it's going to have either dispersion forces, which is seen in all molecules, dipole forces, which is seen only in polar. So polar also has dispersion. Or if you dissolve an ionic compound in water, or some other polar substance, you have an ion dipole force. And that's really it for IMFs. Bonding, generally speaking, based on people who took the test early and fourth block who already took the test, drawing has been mostly good. And I've been pretty pleased with how well we've been drawing, especially since we've been drawing a lot of those ones that break the octet rule. But general tips when you're drawing things. 8 is good. Atoms want to be surrounded by 8 valence electrons. That's called the octet rule, because they want to be like the noble gases. All the noble gases have 8 valence electrons. So 8 is good. Some exceptions are hydrogen is happy with 2. Now, don't actually say happy on a test. That's an analogy, trying to personify these things. You can't say that. Hydrogen is small and therefore only wants 2 valence electrons instead of 8. Boron is happy with 6. And that's really the main exceptions that we do. There's other exceptions out there like beryllium and aluminum sometimes, but the ones that we draw the most are hydrogen and boron. Other tips for drawing. You should count your electrons. More specifically, your valence electrons. your final answer cannot have more valence electrons than what you said it was going to have to begin with. So for example, if you're drawing something like CO2, or we'll do CS2, because people mess this one up a lot. We'll do N2 after this, because people mess that one up too. Carbon has electrons, and each of the sulfurs have 12. So your final answer, each of the sulfurs have 6 for a total of 12. So your final answer should have 16 electrons. The first thing you do is bond them up. Each bond counts for 2 electrons, one from sulfur, one from carbon. So 16 minus 4 is 12. You have 12 electrons left. 2, 4, 6, 8, 10, 12. Put them on your outer atoms, and you're done. Your answer can't have more than 16 electrons, and it does. Your issue here is carbon. The first thing we said is we are happy with 8. And that carbon in the middle only has 4. One from each bond. 2 electrons from each bond. Give it 4. So this is an example of famine. This is when our central atom is looking for more electrons. It's hungry, so we need to feed it. So get rid of a pair from sulfur on each side. Now we're good. So, biggest tips. Draw it. Count your electrons. Make sure every atom has 8. How do you know when you can have more than 8? We don't actually do that many examples. It seems like most of the periodic table, you're going to draw something that has more than 8 valence electrons, because as soon as you hit phosphorus, you can have more than 8. But still, most of the examples we do follow the octet rule pretty good. Something like PF5 is going to break it, because PF5 has 5 bonds. You can't draw those bonds from fluorine to fluorine, or else you're not going to be happy. So, you can break the octet rule when you need to. If you have electrons left over, so like the one we did in the warm-up today was TeCl4. TeCl4 has the 4 chlorines out here. You surround them by their electrons, and then at the end you had 2 electrons left over. So that's feast. That's when you have electrons remaining. You have excess electrons, so you can give that one in the middle those excess electrons. So whenever you're counting and you have electrons left over, just throw them on the central atom. It will be more than happy to take it. Don't forget about SNAP. So in terms of the molecule as a whole, not the bond, this is about the molecule, you have symmetry, nonpolar, asymmetry, polar. So if the molecule is symmetrical, it is not polar. If the molecule is asymmetrical, it's polar. And the easiest way to tell is one of 2 scenarios. You have a central atom, and you have something here, and you have something there, and you have something there, and you have a lone pair. A lone pair on the central atom is a dead giveaway for polar. Because, like I said, we don't get too crazy with the polar and nonpolar stuff. We could, there's a few crazy examples we could do, but we typically don't get there. So as soon as you see a lone pair in the central atom, polar. Or you see something like this. If that central atom is not bonded to the same substance on each side, that is also a dead giveaway for polar, because it's not symmetrical. That carbon, if it looked in each direction, north, south, east, and west, would see a couple of different dudes to his north and east, west, a couple of different dudes to the east and south, and go, oh, those aren't the same, so that's not symmetrical, which makes it polar. Symmetry, nonpolar, asymmetry, polar. Just don't forget to snap. I said we draw N2, so let's draw N2 since people goof N2 a lot. N2, N has 5 valence electrons. There's 2 of them, so that's a total of 10. First thing you do is bond them together. I have 8 left over. 2, 4, 6, 8. I've run out of electrons. The problem is this silly N only has 4 electrons around it. 2 from the bond, and those 2 lone pairs, that 1 lone pair on the bottom. So again, this is famine. That nitrogen's not happy. And when you're not happy, you're going to get rid of a pair on the other guy and keep forming bonds until you are happy. And in this case, you got a triple bond. So N2 always trips people up. Count your electrons, pair them up, you'll be fine. Let's see. Generally speaking, based on the tests I've looked at, based on the tests I've graded, it's been the multiple choice that's really tripped you guys up more than the short answer. There are some tricky short answer. It's chemistry. There's no easy way to get 100. More likely than not, a lot of kids don't get hundreds. There's always very few hundreds in chem. But I would take your time on the multiple choice, read it over, ask questions. I think people get lost in the wording sometimes, and you don't feel like getting clarification. I'm here to help. So, like, if you don't know what a question is asking, obviously I can't, like, spell it out for you. But I can do as much as I can to make sure that you understand it. Because I don't want you to get a question wrong because of misinterpretation. I want to get data about this test that says, we really didn't get blank, not we were tricked on blank. Because honestly, the only other thing that's on the test is ionic versus covalent and naming and formula writing. And ionic versus covalent bonds, we already did a lot in class. We went over it. I know all my classes did this warm-up one, but really quick, ionic is a metal and a non-metal. Ionic transfers electrons. Covalent are 2 nonmetals, and covalent shares electrons. That's what you need to know about ionic and covalent. Don't tell me it's a metal and a metal. We haven't talked about that yet. Will we? Yes. Is it hard? Not really, because we don't get that really into metallic bonding. So this is all the bonding that you know exists right now. There's 2 other types of bonds we'll talk about. Then we'll be done with bonding. We'll be done with this unit that seems to take forever. In it, truth be told, it is kind of long. But we'll get there. Aside from that, the only other thing on it is naming. And all I can really say for naming is if it's ionic, which more likely than not, there will be on the test because the covalent ones are easy. Actually, I don't even know if I give you a covalent one. Check your charges. If you're doing a formula, crisscross them. If you're naming, so like if you're given a formula, and like I said, this was on the warm-up, so I'm not going to spend much time on this tonight either. If you're naming compounds, don't forget the ones in the middle, you need parentheses when you're naming these because they all have multiple charges. And if you have multiple charges, you need to tell me what charge do you have in the parentheses. What charge do you have in the parentheses? So just don't forget that. Aside from that, that's all I really wanted to talk about tonight. If you want to come into my room tomorrow morning, I always get to school pretty early. Feel free to stop by. First block, if any of you kids were awesome to actually check this out tonight, there's like 6 of you that need to take the test. You're going to start it tomorrow. You're not going to finish it in class. Everyone else, since that day, like I said earlier today, I kind of left class. I'm going to give you the opportunity to look over your test. I'm going to give you the opportunity to ask questions on the test. It won't be long, probably like 10, 15 minutes, but do take that seriously. You're rested. You've had a good break. You're going to come back with a fresh mind. You had a lot of tests that final week of school before break, and sometimes you get exhausted. Some of you outright told me you didn't prepare for the chemistry one. I get it. So, take this time tomorrow. Try to get some points back. Everyone else, get a good night's sleep. Third block. Don't stress. You're going to do fine. We'll see you tomorrow.